it's good also for you to try them out, the questions, the sample test questions for to practice. Yeah. So the format for your upcoming test one is almost the same like the one in the samples that I have uploaded. Okay, let me share the content of my computer screen. Let me first share. Okay, I hope you can see this. Okay, yesterday we have discussed some chain rules related to function of several variables here. So there are four types of chain rules that we're going to discuss. We have already discussed cases A and B, isn't it? Yeah, we have already discussed cases A and B here. Next, I will discuss the remaining two cases, C and D. This where okay, are there any questions first regarding the lecture yesterday? Anybody?
For me, so far so good, sir.
Okay. Okay, if there's no questions, let's look at case C. What is case C? Chain rule. Here for case C, again we have z equal to function of two variables x and y. But now x and y, they are in turn functions of new two variables, u and v. Okay. Um, this is sometimes the case when we want, for example, when we want to express x in polar coordinates, y also in terms of polar coordinates. Okay, r and theta. So that means z is a function of r and theta. Yeah. Okay, so we will see one example related to polar coordinates for case C. So z is a function of x and x and y, they are in turn functions of new variables u and v. So that means z is as a whole is a functions of u and v. Okay. So that means we can determine so there exists z partial u as well as z partial v. Yeah. So here is the chain rule for finding z partial u. It is equal to z partial x times x partial u plus z partial y times y partial u. Okay, for z partial v, it is equal to z partial x times x partial v plus z partial y times z partial v. All right, so look at the notations being used here. Everything is in partial derivatives. Okay, there is no straight d involved here. Everything is curly d here because z is a function of x and y, and x is a function of u and v. Y in turn is a function of u and v also. So all the derivatives involved in this formula here, they are all partial derivatives. Yeah. Okay, let's see one example related to case C. Given z, x, l, and y. Okay, so z is a function of x and y here, right? So of two variables. And suppose x in turn is equal to u squared plus v squared. So here x is a function of u and v, and y is equal to u squared minus v squared. Okay, so y is also a function of u and v. So z as a whole is a function of, so if we substitution gives substituting, then we get z equal to u squared plus v squared ln u squared minus v squared. Okay, so z is a function of, after the substitution, you can see that z is as a whole is a function of u and v. Okay, after the substitution here, so we can find z partial u as well as z partial v. We can find z partial u, z partial v directly from here. Okay, for example, what is z partial v u? Can think of this as a product. Use the product rule. So we differentiate u squared plus v squared times ln u squared minus v squared. Okay, and then we differentiate the second function with respect to u. So I'm using the product rule here. So this gives 2u ln u squared minus v squared plus u squared plus v squared. The partial, we want to find the partial u of ln u squared minus v squared. We use the chain rule. It's 1 over u squared minus v squared. And then we find the first we differentiate the outer function, and then we differentiate the inner function with respect to u. We get 2u, right? So the result is 2u ln u squared minus v squared plus u squared plus v squared 2u. Let me write 2u in front. Everything here divided by u squared minus v squared. So that is z partial u. Okay. Yeah. So here we have first expressed z in terms of u and v, and then we find z partial u. Alternatively, we can make use of the chain rule that was shown earlier. You can also calculate z partial u as using this chain rule. This is u, this is z partial x. Z partial x times x partial u plus z partial y times y partial u. Okay, using the formula that was shown here. Yes, using this formula here. So continue. So what is z partial x? Look at the function z. The given function z is x, l, and y. Z is x, l, and y. So let me write it over here as a reference. X, L, and Y. So what is Z partial X? It's L and Y, right? It's just L and Y. And what is X? What is X just now? X is U squared plus V squared. X partial U is 2U. And then Z partial Y is the derivative of L and Y with respect to Y is 1 over Y. So we have X over Y here. And Y, what is Y given just now? It's U squared minus V squared. Yeah. Y partial U is 2U. Okay. So here we have Z partial U involving X, Y, and U. Um, so we substitute, right? Now we substitute. Replace Y by U squared minus V squared. And then we replace, for the second term, we have 2ux. We replace x by u squared plus v squared. Downstairs, we have y. And then we replace y by u squared minus v squared. So you see, we obtain the same answer also using the first approach. You see, the first approach, we do the replacement of x and y in terms of u and v. So we have z totally in terms of u and v. And then we differentiate z with respect to u. Okay, using the product rule here, and then using the chain rule as well. And another method is to use the chain rule given in this form. Okay, so which method is easier? Which method is easier? Yes.
The second method.
Second method is easier, right? It's obvious. The second method is easier. Yeah. Right. Mm. Now, there's a common mistakes, some in writing. Yeah. Sometimes students did not pay attention to the right notation. Sometimes I've seen students, instead of writing the exact using curly D, they still want to write using straight D. So you will get everything in straight D. So this is not correct. This is not the right way of writing. This is not correct. Because everything here in terms of straight D, when in fact you should be using curly D. Yeah. And also there's a temptation to do cancellation here, right? There's a temptation to do cancellation. Delta Z, delta U, cut a copy. Cannot move this one. Well, never mind. There's also sometimes there's a temptation, to cancel out. What happen if you cancel out? Then you will get on the on the right hand side. Okay, then you will get delta z z partial u plus z partial u. So this is saying that the left hand side z partial u is equal to z partial 2 partial u. Right? So if you cancel out z partial u, then you will get this silly equation 1 equal to 2, which is certainly false. Which is certainly false. So this shows that you cannot do the cancellation. Yeah. Cancellation is not permissible. It's not allowed. Yeah, it's not allowed or not permissible here. Okay. Because you must understand what is z partial x here. Okay, what is z partial x? By definition, it is the limit. It is defined in terms of limits f x plus h y minus f of xy divided by h. Okay. If what is f here is to be understood that this is our f xy. This is actually the notion of the z partial x. See, it is not a fraction. It is a limit. It is a limit expression. So how is it possible you want to cancel out? Whereas what is x partial u? X partial u is also in terms of defined in terms of limit, in terms of x u plus h y minus u minus x, because x is a function of u and v, right? Yeah, so by definition x partial u is this limit here. Okay, so they are not simply fractions here. Okay, so that's why such a cancellation is not allowed. If you multiply these two partials, you can see there is no cancellation possible. Yeah, no cancellation is possible here, right? So so this shows that you cannot cancel out as simple as that. Yeah. Okay. We have already found a z partial u. We can also determine z partial v. Yeah. Yeah. So let's continue. What is z partial v from previous exam? Okay. What is z partial v? By the chain rule, it is z partial x times z x partial v, right? And then plus z partial y times y partial v. Yeah. So remember again what is z. Z is x ln y, and x is u squared plus v squared, and y is u squared minus v squared. Yeah. So z partial x is ln y, and x partial v here is 2v. Z partial y is x over y, and y partial v is minus 2v. minus 2v. So next we replace all x and y in terms of u and v. L and y becomes ln u squared minus v squared. We have x over y, so that means we have u squared plus v squared divided by u squared minus v squared. So that is the first partial, z partial v. Okay. So make sure the notations are written correctly. Um, so uh, so it is better to use the chain rule, okay, rather than doing the substitution first. You can see it is better to apply the chain rule straight away rather than trying to express z in terms of u and v first and then find z partial u. As you can see, it is more convenient or more efficient to use the chain rule here. Any question for this example?
I think everything is okay, Doctor.
Okay, thank you. Let's look at an example. Um, hmm. Okay, this is case C, right? Case C here. We have another chain rule. This written here as case D here. So it's just an case D is just an extension of case C from 2 variables to 3 variables. So we have W now in terms of X, Y, Z, where X, Y, Z, they are all in turn in terms of U and V. Okay. So W as a whole is a function of U and V also, right? So that means theoretically it is possible to find W partial U and W partial V. And the systematic way of finding W partial U is W partial X times X partial U plus W partial Y times Y partial U plus W partial Z times Z partial U. Okay, you see that it's almost the expression is almost the same, right, for the two variable case, except that instead of a sum of two terms, now we have a sum of three terms for a function of three variables. And similarly, we also have this last equation here for finding W partial V. Okay, this is yeah, sometimes it is also useful. Sometimes a function of x, y, z, and then maybe, okay. Sometimes we want to work in a different coordinate system. Okay, there are many coordinate system. For example, they have the Cartesian coordinate system x, y. We also have the polar coordinate system r, theta, and there is also the later on you will see um, the cylindrical coordinate system for three-dimensional space, and also the spherical coordinate system also for coordinate space, three-dimensional space. So sometimes when we want to express something in terms of from Cartesian to polar, from Cartesian partial derivatives, and from Cartesian to other coordinate systems. So the chain rule is useful. Okay, let's see an example for case D. Given W equal to square root x plus say y squared z cube, with x as a function of u and v, 1 plus u squared plus v squared, y also as a function of v, u and v equal to uv, and z equal to 3u, 3u here. Okay. So if I use substitution, gives, so initially w is a function of x, y, and z here. So we can think of using the notation used in the theory. You can think of this g1 function uv. You can think of uv as a function of g2 u and v, and you can think of 3u as a third function of u and v. Yeah. So if we do the substitution, then we get w square root x is square root of 1 plus u squared plus v squared, y squared. What is y squared? Y squared is, and z cube. Z cube is 3u cube. Okay. So this is the same as u to the power 3 u squared times u cube, u to the power of 5, and then v squared. So you see, as a whole, w is a function of u and v. Right? So we can, so theoretically, there exists a w partial u and w partial v. Yeah. So we can determine w partial u, w partial v directly from the expression w in terms of u and v. Okay, let's try. Let's apply the chain rule. Okay, applying the chain rule. V partial x is 3. The first partial derivatives w with respect to u and v. So what is, so first we want to find w partial u. So we have w from the chain rule. This is w partial x times x partial u plus w partial y times y partial u plus w partial z times z partial u. Okay. And w partial x is what? What is w partial x? Anybody? Yes? Anybody?
1 over 2 square root x.
Yes. 1 over 2 square root x, yeah? So you need to know your basic calculus very well. Okay, that's all, right? That's all. X partial u is 2u, right? 2u. What is w partial y? It's 2y z cube, right? 2y z cube, and y partial u is v. W partial z is 3y squared z squared, and z partial u is 3. Okay, and the last step is to, so here we have w partial u in terms of x, y, u, and v. So the next step is to replace u and x here, x and x, y, z in terms of u and v. So notice that here 2 cancel out. So here we have u. And then recall that x is the same as 1 plus u squared plus v squared. We have 2 y. What is y? Y is u. V. What is z? Z is 3u. Okay. Times v. Then again replace y. For the third term, replace y by uv. We have 3 times 3, that's equals 9. And then z squared. Z is 3u squared. And then the remaining work is just algebra. Okay, it's just algebra. This is equal to what? 27 times 2, that's 54. We have u times u to the power of 3, u to the power of 4, v times, and then we have v squared. Yeah. For the next term, 9 times 9 is 81. We have u squared times u squared, so u to the power of 4, and then v squared. Okay. So the second and the third term, they are like terms, so we can combine them. So the result is u divided by square root 1 plus u squared plus v squared plus, what's that, 135, isn't it? 135 u to the power of 4 v squared. Okay, so that's w partial u. So the other possible first partial is w partial v. So this is the formula. It's the same as w partial v, but with u replaced by v. Okay, I leave it to you to show that the result is v over square root of 1 plus u squared plus v squared plus 54 u to the power of 5 times v. Okay, I leave it to you to show that, to show this result. All right, so those are the 4 types of chain rule that we have discussed, which I have indicated here as cases A, B, C, and D there. Okay, let's see one question from sample test 1. I have uploaded the sample to the e-learning. So let's see one example. Let's try one problem here from this sample test 1. Okay, so let's take this problem as our next example. This is sample test 1 question here. Given z equal to fuv, where u is 2x cosine y and v is x sine y. Find z partial x and z partial y. You see, they turn around the rule of uv and xy. You see, in our previously in our theory, we let z equal to fxy, and then let x in terms of u and v, and also y in terms of u and v. But here they have, they have twist the notations here. So here z is in terms of u v, where both u and v they are in terms of x and y. Yeah. So z as a whole is a function of x and y. So there exists z partial x and z partial y. So use the chain rule. We use the case A, right? We apply the chain rule, case A. Yeah. The one that we have discussed is we have 4 cases. So here case A is relevant. Oops. So what do we need? Z partial x. So z partial x is z partial u times u partial x. So this is the right way of writing it. Z partial v times v partial x. Okay, this is the correct way of writing z partial x. Yeah. F is arbitrary here, so there's nothing we can do to write to find z partial u, because z is arbitrary. So z partial u remains the same. What is u partial x here? U is 2x cosine y. So u partial x is what? 2?
2 cos y.
2 cosine y, yeah. Z partial v remain the same, because z is in terms of any function f u v. So we retain z partial v the same. Next is v partial x. What is v partial x? This is v partial x in terms of xy. So v partial x is
Sin y.
sine y. Okay, yeah. So let's rewrite this the result as 2 cosine y times I can also write z partial u as z subscript u. Okay, maybe it's easy to write z with subscript u for z partial u, then plus sine y times z partial v. Okay, let me use subscripts for partials here. So the left hand side, I can also write it as z subscript x or z partial x. Yeah. Okay, next we want to find z partial y. So z partial y. Okay, using the shorthand notation. Um, z partial y is z partial u times u partial y plus z partial v times v partial y. Z partial u remains the same. U partial y. What is u partial y? Yes. What is u partial y here? Minus 2x sine y, right? It's minus 2x sine y. Next, we have z partial v times v partial y. Look at v. V is equal to x sine y. So v partial y is x cosine y. So,
Apa tu? Macam mana saya nak ingat benda ni?
siapa tu? So let's rewrite this result as minus 2x sine y z partial u plus x cosine y times z partial v. Okay? Yeah. But we are not done yet. There is another part. Hence. You see, the word used is hence. Yeah, hence. What does it mean, hence? Hence, show the following equation is true. Yeah, so that means whenever you see the word hence, that means use your results, your previous results, to prove the next result. So previously we have obtained z partial x and z partial y. So we want to show the given equation there is true. Okay. They all involve square, isn't it? We have found z partial x. We also have found z partial y. So one way is to work from the right to the left. Okay, let's work from the, because we have found z partial x, we have found z partial y. So let's work from the right to left. Yeah. What is, okay, we need the square. Okay, we need the square of z partial x. What is that? This 2 cosine y z partial u plus sine y z partial v squared. Okay, the square is 4 cosine squared y zu squared plus 2, 4, right? 4 cosine y sine y zu z partial u times z partial v. Then finally we have sine squared y times zv squared. Okay, so that is the square of z partial x. Next, we will also want to find the square of z partial y. Why we want to find the squares? Because the equation involves squares of z partial x and z partial y. So, what is the square of z partial y? Can we do it directly? it's 4 x squared sine squared y zu squared plus minus 2x minus 4 minus minus 2x, so minus 4 x squared sine y cosine y zu zv, and finally x squared cosine squared y, and then we have z partial v squared. Okay, so we have found z partial x squared and z partial y squared. But look at this, for the square of z partial y, we have this coefficient 1 over x squared. So that means divide both sides by x squared. From the result that we have obtained just now, we divide both sides, can factor out x squared. So that gives 4 sine squared y zu squared minus 4 sine y cosine y zu zv, z partial u, z partial v plus cosine squared y times zv partial v squared. Okay, next we want to form the sum. Okay, the right hand side is the sum of z partial x squared. The right hand side is z partial x squared plus 1 over x squared z partial y squared. What happened to the sum? We want to find the sum of this term with this term. These are the two like terms, so we can combine them, right? What is we can then we have cosine squared plus sine squared. We can factor out 4 z partial u squared. In the bracket we have cosine squared plus sine squared, which is 1, right? So in forming the sum, we use this identity here. So we get 4 z u squared, 4 z partial u squared. And look at the next term. They're the same but with opposite sign. So the sum is 0. Okay, when you add them up, they are equal but one is of opposite sign. So the sum is 0. And lastly, we have these two terms that we wish to combine. Again, using the identity that gives a z partial v squared. That is what we want to prove, isn't it? That is what we want to prove here. 4 z partial u squared plus z partial v squared. So that completes the proof. Any question? No, doctor. Tak ada. Okay, let's see another example. Oh, okay, let's have a 10 minutes break. It's already 11:51. Let's have a 10 minutes break.
Sir, can you move up a bit.
Okay. Scroll up, you mean?
Yeah, okay, thank you.
All right. You want to have a 10 minutes break or I'll just continue? If I continue, we can stop at 12:40.
We have to have a break for 10 minutes.
You want to have a 10 minutes break?
Yeah.
Okay.
Thank you, doctor.
Go ahead then. Yeah, let's have 10 minutes break. Okay, welcome back everyone. Let's continue the lecture. So let's discuss another sample test 1 question related to chain rule. This is also a sample test 1 question given w xy equal to x squared plus 2y squared with r with x equal to r with x equal to r cos theta and y equal to r sine theta. Okay, so w is in terms of Cartesian coordinate xy, where x and y they are in terms of polar coordinates here. Okay, so both x and y here are in polar coordinates, r theta here. So use the chain rule to determine w partial theta at the point r theta equal to 1, 0. That is the question here. So we use the case C, okay? Here we use the case C, apply case C, chain rule case C. So first we write it as w partial theta equal to w partial x times x partial theta, then plus w partial y times y partial theta. Yeah, this is what that need to be written down first. In order to get marks, this must be written down. Yeah. And then do the partial derivatives. W partial x is 2x, and x partial theta is minus r sine theta, and w partial y is 4y, and y partial theta is r cosine theta. Okay, So this is, so and then we replace x by r cos theta, y by r sin theta. So this gives what? X is r cosine theta. So that gives a minus 2 r squared cos theta sin theta. And then replace y by r sin theta. So we get 4r squared sin theta cos theta. So the sum can be simplified to 2r squared. 2r squared sin theta cos theta. Okay, so that answers the first part. Now we want to determine the value of the partial derivative w partial theta at the given point r theta equal to 0, 1. So we replace r by 1, 0. Yeah, we replace r by theta by 0. So the result is 0 then, because sine 0 is 0. So the answer is 0. Okay, so that is the way to solve it. Yeah. If you see in case w, just a remark here, even though it is not required by the question, just a remark, in case we want to determine w partial r, then it is w partial x times x partial r plus w partial y times y partial r. Okay, in case w partial r is required, so this is the chain rule that need to be used. Okay, I leave it to you to what to determine w partial r here. Any question for this question?
Doctor,
Yes.
how many marks for this question?
Uh, I don't remember. I can't remember. Maybe 5 marks or something like that. Yeah.
Oh, okay.
Okay. Mm. Okay. Yeah. If you are able to write this partial derivative, chain rule correctly, then you will get some marks. Yeah. If you are able to find the partial derivatives then correctly, then you will get additional marks also. If you manage to get this answer correctly, then of course you will get 1 mark. And then if you manage to get do the to determine to be able to do this substitution correctly, to be able to get this answer correctly, then you will get marks also. Yeah. Okay, next is about implicit differentiation here that I want to discuss with you is because if you look at the sample test 1, there's a question related to implicit differentiation here. Suppose z is a function of x and y, but it is not, the function z is not defined explicitly in terms of x and y. It is here defined implicitly by this relationship here. So how do you determine z partial x? Okay, so for this example here, z is defined explicitly, right? In this question, z is defined explicitly in terms of x and y. We have z alone on the left hand side, and we have an expression in terms of x and y only on the right hand side. So this is z. We say z is defined explicitly in terms of x and y, but however, in this equation, uh, z is a function of x and y, but it satisfies this relationship here. If you look at this equation, it is hopeless to solve for z, right? There's no way we can solve for z from this equation. But however, it's still possible to determine z partial x, z partial y using chain rule also, using chain rule. So let's discuss this topic next. So as an example, we have this implicit differentiation. Implicit differentiation. So suppose y. Okay, let's look at what we have studied in calculus before. Right? In calculus, suppose y is defined. Y is a function of x defined implicitly as defined implicitly as this relation x squared plus 2xy minus 3y squared equal to 6. Okay, so we want to determine dy dx. I think you have solved this before, right? In your previous calculus class, you have a function y defined implicitly through this relationship x squared plus 2xy minus 3y squared equal to 6. You still remember how to determine dy dx here? We differentiate both sides, right, with respect to x. D, we differentiate both sides with respect to x. So we get 2x. We have 2xy. So here we use the chain rule. The chain rule. I mean the product rule. We differentiate 2x, we will get 2 times y, and then 2x times dy dx, and minus 6y times dy dx, and on the right hand side is 0, right? Oh, battery is running out. Okay. And then we solve for dy dx from this equation. So we write this as 2x minus 6y times dy dx. And the terms independent of dy dx, we move it to the left hand side, to the right hand side. So we get minus 2x minus 2y. And then we solve for dy dx. So it's minus 2x minus 2y divided by 2x minus 6y, which can also be written if I multiply and divide by minus a half, then I will get x plus y divided by 3y minus x. Okay, that is the answer here. Hmm. This is one way of finding dy dx. I'm sure you have learned this before in your previous calculus class. But now I want to show you another method using partial derivatives. Now that you have learned partial derivatives, we can also solve this problem using partial derivatives. Okay, alternative method using partial derivatives. If we have a function fxy, suppose we have a function fxy defined implicitly through this relationship. Okay, yeah, you see here, we can think of this function here as a function of x and y, as a function of fx and y, right? Can think of that function, the expression on the left as a 6 is just a constant on the right hand side. So you can think of the expression on the left hand side as a function of x and y, where y is a function of x. Okay, y is a function of x. So remember the chain rule that we have discussed. Where is it? Yeah. So think of this as a function of u and v. Okay. Uh, we 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 rewrite this. Uh, we rewrite this as a function of u and v. Suppose I now write it as a function fuv with u is equal to x and v as a function of x. Yeah. I rewrite the function fxyx equal to 0 as f u v equal to 0, with u as a function of x and v as a function of x. Now we differentiate. So remember, f as a whole is a function of x. So I can differentiate both sides with respect to x. Now we apply the chain rule. We apply the chain rule. So on the left, we get f partial x times f partial u. I'm sorry, f partial. What is it? F partial u. Yeah, f partial u times u du dx. Okay, times du dx. Yeah, I'm using
Doctor,
straight. Yeah,
may I ask a
uh,
question?
yeah.
May I know where the zero come from?
Zero.
Yeah,
Oh,
yeah, is it 6 or 0?
no. This is I'm talking in general here. Okay. Okay. You see, this
Yeah,
equation.
it's and confusing, sorry.
The, you see, this is equivalent to x squared minus. What happened here? X squared. I can write it in this form, right? Isn't it?
Yeah, yeah.
So this function on the left hand side can be viewed as a function of x and y, two variables x and y. Okay.
Oh, I see.
Yeah. So
Okay, okay.
so in general, um, the implicit function, if y is a function of x, so if y is defined implicitly, it can be rewritten in this form in general. Okay, in general, it can be rewritten in this form here. So I'm discussing here a general situation here. Okay. Mm. All right. Then we have here. What else? Okay. Next is what? F partial v. Next we have f partial v times dv dx. Okay, dv dx. Yeah, equal to 0, right? Equal to 0. Okay, now recall that this is using case A. Case A, okay, partial derivative, uh, case A type, yeah. But remember, u is equal to x. So then we have f partial u is equal to x, right? So I now replace u by x in the above equation. And f is y, okay? And v is equal to y. So I can replace v by y. Yeah, all right? That what happens. And this is equal to 1. So now I can solve for dy dx from this equation. I can solve for dy dx from this equation. So dy dx, if I solve for dy dx, it is equal to minus f partial x divided by f partial y. Okay, so this is another formula to compute dy dx if y is defined implicitly as fxy equal to 0. Right. So let's try this formula for our previous example. Um, So in the previous example, given, what was it given? Just we have x squared plus 2xy minus 3y squared equal to 6. Okay, we want to write it in the standard form, fxy equal to 0. So we rewrite this as x squared plus 2xy minus 3y squared minus 6 equal to 0. Now let's call the expression on the left here as a function of two variables, x and y. So using the green box formula, dy dx is minus f partial x over f partial y. What is f partial x? Anybody? What is fxy here? It's x squared plus 2xy minus 3y squared minus 6.
Uh,
So f partial x is
2x plus
2x
2y.
plus 2y. That's all, right?
Yeah, that's all.
That's all. And what about f partial y below?
2y minus 6y.
No, try again.
2x.
2x, yes.
2x, sorry,
Yes,
Minus
yeah.
6y. Minus 6y.
Minus 6y, okay? So
6y.
now we divide both numerator and denominator by 2. We will get minus x plus y upstairs. Downstairs we get x minus 3y. Is it not the same with our previous result? The same, right? Previously we got x plus y, 3y minus x.
Yeah.
Yeah, if I multiply this negative sign into the denominator, we have a minus sign in front here. So if I multiply that minus sign into the denominator, we will get 3y minus x, which is the same, right? From the previous method. Yeah. So this is one application of partial derivatives for finding dy dx, where y is a function of x defined implicitly. Okay. So let's look at a sample test question. Yeah, this one. Is it this one? Do I have? Yeah, this one here. Okay, look. Let's try. Okay, using the partial differentiation method to solve this problem here. No, this is. Oh, this is a function of three variables. Z. It's a function of three variables. Okay. This one involves function of three variables. So similarly, let me show how this method also works for function of three variables. Okay. Similarly, if z is a function of fxy, if z is a function of x and y defined implicitly as f x y z equal to 0, then then z partial x can be defined as f minus f partial x over f partial z, and z partial y is equal to minus f partial y over f partial z. Now, this is the extension of the previous formula to a function z of two variables x and y defined implicitly as fxyz equal to 0. This also can be defined from this also can be determined from our chain rule. The chain rule. So how to prove this? Let me prove this. Recall. Suppose here is the proof. Suppose we have f yeah. Suppose f is a function of u and v, u, v, and w, where u is equal to uxy and v is a function of vxy, and similarly w is a function of x and y. So f as a whole is a function of x and y, right? So by the chain rule, we have f partial x equal to f partial u times u partial x plus f partial y times y partial x, isn't it? Oh no, this is v. F partial v times v partial x plus f partial w plus f partial no, w partial x, right? Yeah, by the chain rule. Case here I have used case D. Case D, yeah. So now suppose I replace now u equal to x, v equal to y, and w as a function of x and y. W here as a function of x and y. So what happens? What happened? We have f partial x on the left equal to f partial x times partial x. What else? F partial y, because we will replace y by x, and then f partial z times z partial x. All right, that is the result. Now, by hypothesis, fxy equal to 0. This is the hypothesis, right? This is the hypothesis, the condition. So that means the left-hand side is 0. Yeah. And this is equal to 1. So we have f partial x there. And y partial x is 0, right? Y, here. This is 0 because y is a variable, x is also a variable. So this is 0. Yeah, this is 0. And then we have 0, and we have f partial z, z partial x times z partial x. So now we solve for z partial x. So that gives minus f partial x over f partial z. So that proves the first partial derivative here, this one here. That proves this formula first for the first partial for z partial x. Okay, so similarly, it can be shown that z partial y is equal to minus minus f partial z y divided by f partial z. Yeah. So now we can solve that question that I showed you just now from the test. Which one is it? This one? Yeah, this one. Okay. So let z be defined implicitly as a function of x and y by this relationship here shown. So find z partial x. Okay? Find z partial x. So first we rewrite the given equation as we rewrite this given equation so that the right hand side is equal to 0. So then we have e to the power of yz times sine xy plus y times e to the power of z plus 2 ln x minus 2 minus 3 ln 2 equal to 0, right? So so the so the expression on the left is a function of three variable, capital F, X, Y, and Z. Yeah. So here Z is a function of X and Y, but defined implicitly according to the given relation there. So as you can see, it is hopeless to solve for Z, isn't it? It's not. I don't know how to solve for Z in terms of X and Y. So nevertheless, we can still determine z partial x from the given formula that we have derived. It is minus f partial x divided by f partial z. What is f partial x? Look at terms containing x only. We have sine, right, containing xy. So if we differentiate that with respect to x, treating y as and z as constant. So you get e to the power of yz. Sine, we differentiate sine, we get cosine. So the outer function is cosine. And then we differentiate xy with respect to x, we get y, right? We get y. Okay, y times e to the z. There is no x there, so it's 0. 2 ln x. Differentiate ln x, we get 2 over x. The remaining are just constant. So that's all there is for f partial x. What about f partial z? Anybody want to try?
YE
Oh,
to the power of
Yes.
YZ
Uh-huh.
sine XY
Y e to the power of yz times, okay, sine xy, that's correct.
plus
Lima,
YEZ.
ye to the z. Anything
Ah,
else? No
nothing.
more, right?
Zero.
No
Yes.
more. So that is the answer. Okay, so that is the answer for z partial x. You see that it contains z. Okay, the result contains z, but that is normal. If you if z is defined implicitly, normally the result also contains z. Yeah. Okay, let's suppose it is required to find z partial y. Okay, the question here did not ask for z partial y, but let's try. It's equal to f partial y divided by f partial z. Yeah. What is f partial y?
E to the power of YZ cos XYX.
Mm, hmm? You want to differentiate with respect to y,
Z.
you have to use like a product rule, isn't it? You have to use a product rule because the exponential term contains y, the sign also contains y, right? So you have to use the product rule to this term because the exponential contains y, the sign also contains y. So use the product rule. So that means what? I will first we differentiate the exponential with respect to y, we get z, right?
Z,
We get
Z
z
exponential YZ,
e to the power of yz
Z,
times sine, isn't
sine,
it?
yes, sine
Sine
XY,
xy and then plus,
plus exponential YZ,
okay,
cos XY times X,
cos xy
times X.
times x, okay?
Yes.
So here we need to use the product rule.
Yeah.
Okay, what else?
Plus exponential Z.
Exponential z. That's all, right?
Yeah.
That's all. Okay. And f partial z is the same like what we have calculated above. So this is the solution. See, again, it contains z. But that is usually the case, if we have z defines implicitly in terms of x and y. Just like this example here, you see, y is defined implicitly in terms of x. And look at dy dx, the answer contains y. So that is normal. That's usually the case. Dy dx also here, the result dy dx contains y if y is defined implicitly through a relation. Okay, so that's about the implicit, the application of partial derivatives for finding partial derivative of functions that's defined implicitly here. Okay, so I guess that's all for today. So next week I will discuss these applications. These applications. If you look at our, if you look at our course informations, we look at the course information. I have discussed the domain, range, partial derivatives, chain rule, implicit differentiations. That's in the And then week 3, I've also discussed the week 3. I have not discussed week 2 materials here, but I have discussed the week 3 materials and also the week 4 materials here, right? Yeah, but I didn't follow this strictly. I think so. Next week I will discuss this week 2 materials here. Applications of partial derivative, rate of change, increments, total differential, extrema. Yeah, so if you look at the sample test 1 question last year, we have here questions 5 and 6. Yeah, so these are the topics for question 5 and 6 is what I will discuss next week. Yeah, what I will discuss next week. Yeah. Okay, that's all for today. For information, I've also created the portal in the e-learning for submission of first assignment. Yeah. Uh, uh, so tomorrow I'll give you the next assignment. So before we stop, let me show you the QR code for the
Doctor, how many
attendance.
assignments we can have all the 2 semester?
What?
How many assignments do we have through the semester?
Oh, I don't know yet. It depends on how we progress. Okay.
Okay.
So there is no fixed amount. I said, okay, there's only 5 assignments. No, I don't do that. When I give a course, I don't fix the number of assignments. It depends on how our class, progresses. Yeah. Okay, let's now find the QR code for your class today. Okay, here it is. Yeah, please scan this QR code for your attendance.
You, Doctor.